In this video, we're gonna find out what is differentiation. To understand what is differentiations, let me guide you through the process of understanding what is velocity or speed. Okay, when you ride a car, if you look at the speedometer, you might see a number indicating the speed of this car at a certain time. Well, actually at the time when you look at the speedometer. So what is speed? Normally, if you want to compute speed, you require two different times. So for example, from time t1 to time t2, you will define the quotient of the difference between st2 and st1 over the difference of time between t2 and t1 to be the average speed of the car. Right, so this quotient is actually the slope of the line connecting the two points of the graph of the distant functions. This is actually a secant line of the graph of the distant functions. Well, so in this formula, actually we only care about the difference of the distant function based on the difference of time, right? So instead of writing t2 and t1, we just let to denote t2 minus t1 by h, which means the difference between time, and then the denominator becomes s of t plus s minus st. So this actually reminds us of difference quotient of the function s. Okay, so now v is actually the difference quotient, but well, it's rarely the case that v is the same when we change h, right? For example, here, where instead of considering the time from t1 to t2, let's move t2 closer to t1, then actually the secant line will be varied. And for this reason, we see that, well, the average speed is not the same for all different period of time. And that's the first thing. The second thing is that at a certain time, when you look at the speedometer, then the speed that you see actually correspond only to the moment that you looked on, right? Because and it makes sense too, because when the car is moving, then why do you need to consider two different time in order to know what is the speed of the car? So the reason why we need to pick two different time, t1 and t2, in order to compute the average speed is because now if t2 become t1, meaning that we have no difference at all between them, then h becomes 0, and you know that we cannot divide anything by 0. So that's pretty much the reason why we need to consider two different time, t1 and t2, in order to compute the average speed. But by now we already know the definition of limit, right? So, well, instead of taking a single difference quotient once at a time, if you actually want to know what is the speed of the car at the time t, okay, then instead of taking the difference quotient, we can just try to take the limit of that difference quotient, letting h tend to 0, because when the two times getting closer and closer to each other, then actually you get a closer and closer look at the speed at the time t. So now we can define the limit of the car at the time t as the limit of the difference quotient st plus s minus s of t over h when h tends to 0. Okay, so what is the meaning of Vt? Well, if you look at the difference quotient at the slope of a secant line connecting two corresponding points on the graph of the distant functions, you see that when we let h tend to 0, then the secant line also move. And because it is moving, then its slope is also changed. Then you see that when we take the limit of the slope, then the secant line are also arranged into a limit position, and that limit position will now have a slope Vt. right? So the slope vt actually determining a line to the graph with coordinate t as t, and it actually touching the graph, and that is the meaning of the speed. Okay, so this actually an example that shows us what is differentiation. Now, instead of taking the distance function s, we can take any kind of function f and taking the limit of difference quotient f of x plus minus f of x over h. If that limit exists, we denote it by f prime of x and call the derivative of f with respect to x. Well, we might also denote the derivative of f with respect to x by d over dx of f of x, or in many cases, as we often write y equal f of x, we can also have the Leibniz notation dy over dx for the derivative of the function y equal f of x with respect to x. Or still, we can just simplify the notation by writing y prime for the derivative of y with respect to x when x is understood from the context. Okay, so now comes the definition of derivative. So for function y equal f of x, the limits of difference quotient f of x plus h minus f of x over h when h tends to 0, if exists, is called the derivative of f of x or with respect to x. And the following notation can be used interchangeably to indicate the derivative of f of x, the Leibniz notation dy over dx, or d over dx of f of x, or f prime of x. So it depends on the situation that we can use one of these notation interchangeably in order to make the context clear. If the derivative of f exists, then we also say that f is differentiable at x, and we call f prime. We see that f prime actually looks like a function on x, right? So we call f prime the derived function. And since we can actually consider f prime as a function, we might also need to evaluate f prime. To evaluate the derivative of f at a number t, then we might use one of the following interchangeably. Dy over dx with subscript x equal t, and similarly for the other Leibniz notation, or we just might simply write it as f prime of t. Okay, so now let's get back to the meaning of the derivative. Recall that the difference quotient actually gave us the corresponding slope of the secant light, and because by computing the derivative, we are taking the limit of all of these slope by fixing p and let the other endpoint vary, then actually we know that the derivative of y with respect to x evaluated at x equal the coordinate, the x coordinate xp of the point p, is actually the slope of the limit line of all of the secant line with one point p. So this is actually the line that is tangent to the graph. And well, for this reason, we call the derivative of y with respect to x evaluated at x equals p the instantaneous rate of change of y at xp, or maybe more simple, just rate of change of y at xp. So instantaneous rate of change, or rate of change, meaning the derivative of the function at a certain point. So now come the reverse definitions. If the function f is differentiable at x equal t, then f prime of t is called the instantaneous rate of change of f at x equal t. Let me also recall that a secant line is a line connecting two points on the graph of a function fx, and a tangent line to the graph f of f at a point P is actually the limit of secant lines of the graph connecting P to other points on the graph. So for this reason, if the function f is differentiable at x equal t, then f prime of t is the slope of the tangent line at the point with coordinate t, f, t on the graph of f. And it also means that if f is not differentiable at x equal t, then at the point t with coordinate t, f, t, there is no tangent line to the graph. Okay, so let's see some example how we can compute the derivative. Now let's get started with the most simple thing, the constant functions, fx equals c. So in order to compute the derivative of f, we just need to compute the limit of the difference quotient, which is in this case c minus c over h, and is nothing else but 0. It means that f is differentiable at all real numbers and f prime of x is 0. Let's move on to some kind of more complicated functions, a linear function fx equal x. And similarly, if we consider the limit of difference quotient, now it is actually the limit of h over h, which is always 1. So for this reason, the linear function fx equal x is differentiable at all real numbers x, and the derivative of f is the constant function 1. And similarly, we can consider any other linear function and try to compute the derivative of that. Okay, so as you see, the derivative of f is actually computed at the limit of difference quotient fx plus h minus fx over h. And so we might purposely see that when h tends to 0, meaning that x plus h tends to x, then the limit exists, mean that f of x plus h somehow must tend to fx. So this has something to do with the continuity of f, right? So more precisely, now suppose that fx is a function that is differentiable at x equal t. This means that the limit of ft plus h minus ft over h when h tends to 0 exists, and we denote it by f prime of t. Well, when h tends to 0, then that quotient should tend to f prime of t. It means that when h tends to 0, intuitively we must have that ft of h tend to ft too. And let's see why this actually true. Now let's write this at the limit of fx minus ft over x minus t when x tends to t. So because of the definition of limit, we see that for all delta greater than 0, there exists a positive number epsilon, so that whenever x is close to t with respect to epsilon, meaning that the absolute value of x minus t is less than epsilon, then the quotient of x minus ft over x minus t is close to f prime of t with respect to delta, meaning that the distance between them is less than delta. And from this, we see that the absolute value of the quotient of fx minus ft over x minus t is strictly less than delta plus the absolute value of f prime t. And because when we're taking the limit, we never allow x to be equal to t, then x minus t, taking the absolute value, is always positive. So we can multiply both sides without changing the direction of the inequality, and yet fx minus ft, absolute value of that is less than the product between absolute value of x minus t times delta plus the absolute value of f prime t. So now as we see, if x tends to t, meaning that the absolute value of x minus t getting closer and closer to 0, then Of course, the fx minus ft, if you take the absolute value of that difference, it also gets closer and closer to 0. It means that the limit of f of x when x tends to t is actually ft. So this actually is a definition of the continuity of f at x equal t, right? So for this, we know that differentiability implies continuity. Okay, so we are now ready to list some of the differentiation techniques. Let fx and gx be function differentiable at x equal t. Okay, so we see that the derivative of f plus g evaluated at t is actually the sum of the derivative of f and the sum of derivative of g evaluated both at t. And also the same apply for the difference. The derivative of f minus g is the derivative of f minus the derivative of g. But for the product, we have the Leibniz rule, which is a little bit more complicated. So the derivative of the product of f and g is actually the sum between the derivative of f times g plus f times the derivative of g. And now actually, if g of t is different from 0, we can also say about the derivative of the quotient f over g. For this, we actually can easily deduce the formula for quotient from the formula for product by first noting that if you want to compute the derivative of f, then we can write f as f over g times g, provided that g is different from 0. Okay, so now actually, because it is the derivative of a product, we can use the Leibniz rules. So in the final result, we see that the derivative of f over g is unknown, and this is exactly what we want to compute. On the other hand, g, f over g, and even the derivative of g are known. So from this, we can easily deduce that if gt is different from 0, then the derivative of f over g evaluated at t is actually the quotient, and on the denominator we have the derivative of f times g minus f times the derivative of g divided by g of t squared. Okay, so let's try to apply these properties, the techniques, in order to compute some specific example. Now let's try to compute d over dx of x squared. Okay, so x squared is nothing but x times x, so we can use the product rule in this case. So that's the Leibniz rule that we need to compute. And because we know that d over dx of x is 1, then the final result should be 2 times x. And what about the derivative of x power 3? Well, this can be considered as the product of x and x squared. So you already know that the derivative of x is 1, the derivative of x squared is 2x. So you can easily get that the derivative of d over dx of x power 3 is 3 times x squared using the Leibniz rule. And in general, you can also compute the derivative of x power k for any positive integer k, which is k times x power k minus 1. This might be very familiar to you, but I recall here, based on the techniques that we already learned, to go from the derivative of x to the derivative of x power k for positive integers k. Okay, so that is for power of x with positive power. What about negative powers? Let's take a look at the derivative of 1 over x. Of course, now it is the derivative of a quotient. Okay, then we can use the formula. Here f is 1 and g is the linear function x. So we can easily find out that in this case the derivative of 1 over x is actually minus 1 over x squared. and 1 over x is actually x power minus 1, right? Okay, so that means that d over dx, or the derivative of x power minus k, is actually minus k times x power minus k minus 1 for positive integers k. So we conclude that actually for our integers k, we have a unified formula saying that the derivative of x power k is actually computed by k times x power k minus 1. And not only for integers power, we can also extend this rule to rational power and even real power. Well, to achieve this goal, we just need to recall the definition of composite function and introducing some other techniques for computing the derivative of composite functions. Okay, so recall that if we have a function f from x to y and a function g from y to z, then we get the composition function z round f from x to z, which can be defined by using the formula. So g round f evaluated at x is nothing but g evaluated at fx. It means that we can consider f and g like bridges from place to place. So f is the bridge from x to y and g is the one from y to z. So for a point x on the place x, capital X, if you travel along the bridge f, you get f of x. And again, now fx is inside y, then you can use the bridge g to travel from y to z, and for this fx now become g of f of x. So that is the meaning of composite functions. To understand what a composite function is, let's take a look at a real-life example. Now, you might possibly buy a shoe once, right? And when we want to choose a shoe for yourself, the first thing you need to consider is finding out the size that's the most suitable for you. Okay, and very often you find a lot of different size on a shoe. It depends on where the shoe is produced and where it is internationalized. So for this reason, there might be different standard for checking size. So for example, you have the USA standard, you have the French standard, and Japanese standard for determining size. Okay, so in the example, we see that 11 1 over 2 in USA standards is the same as 46 in French standard, and the same as 295 in Japanese standards. Okay, so how can we determine the size of the shoes in our favorite choice of size? For this, we need to have a table that helps us to convert from one size to another. So for example, in the US standard, we have 8, 9, 10, 11, etc. And in France, we have 41, 1 over 2, 1 over 3, 42, 2 over 3, 44, 45, 1 over 3, and 46. And for Japanese system, we have 260, 270, 280, 290, and 295. So for example, if you want to convert from the US to French standard, then actually you have the function g of x. And if you want to convert from the French standard to Japanese standards, you have the function f. So now suppose that you only have the US standard size. You want to know what is the Japanese corresponding size. Then that is where we take the composite function. So f round g of x is actually the function you need in order to convert directly from the US sign to the Japanese signs without passing through the French signs. Okay, so that actually the meaning of composite function. And now let's actually compute f composite by g. Okay, so from the definition, we see that f round g of x is actually f evaluated at g of x, right? So f of x is 15x minus 100 over 2. Then in order to compute f of g of x, you need to substitute 4x plus 92 over 3 for x into the formula. And we get that formula of f round gx. And you can easily simplify this to get 10x plus 180. So that actually the formula for you to convert directly from the US signs to the Japanese sign. Okay, so that is for the composite functions and why we care about them. Now let's get a look at how we can take the derivative of a composite functions. This is called the chain rule, meaning that if g is differentiable at x equal t and f is differentiable at x equal gt, then the derivative of f round g is actually the product between the derivative of f evaluated at gt times the derivative of g evaluated at t. That is called the chain rule. Okay, so this is the formula depicting the rule. Let's see how we can actually use the chain rule in order to compute the derivative of the power of x in case the power is not integer but is rational and maybe also real numbers. Okay, so let now k be a non-zero integer. Let fx denote the power function x power k, and let g denotes the function x power 1 over k. Then actually we have that the composite function f in g is actually the linear function y equal x, right? So by taking the derivative of both sides of the equation, we get that 1 is equal to the derivative of the composite function f round g. Using the chain rule, we now know that it is the product between the derivative of f evaluated at fg at g of x times the derivative of g. Okay, so the derivative of g is the derivative of x power 1 over k, which is actually what we want to compute. But the derivative of f evaluated at g of x is something we can already compute because k is an integer. So this actually is k times x power 1 over k times k minus 1. Okay. Well, from this we can easily deduce the derivative of g, which is 1 over k times x power 1 over k minus 1. Well, similarly now, if we let f to be x power m and g to be x power 1 over k, we see that the derivative of x of power m over k is actually m over k times x power m over k minus 1. And because every rational function can be written as a quotient of m over k, so we are done verifying the rule for taking the derivative of x power any rational number. So this is the rule. For any rational number q, the derivative of x power q is actually q times x power q minus 1. Okay, so if we want to extend this rule for real numbers, so we need first to decide what is x power r, where r is a real number. Note that for any number r, there is a sequence of rational numbers such that the limit of that sequence is actually r. So because we already know how to define x power a rational number, right? So we can define x power r as the limit when n to tend to infinity of x power q of rn of q sub n. Okay. Okay, so using that, we can also deduce the general rule for computing the derivative of x power r for any real number r as r times x power r minus 1. Well, we do not get involved in the detailed proof of this because it might require a little bit of theory that is way beyond the scope of this course, so I will not talk about this in detail, but we can see that we can use this kind of rule whenever R is a real number. Okay, so you might now want to pause the video and try to compute the derivative of 3x plus 2 power r for some real number r. Okay, so that might look a little bit unfamiliar because it's not actually the power function x power r, but 3x plus 2 power r. But if you look closely to this, there is nothing special about this. It's actually the composite function, where the first function is x power r and the second function is 3x plus 2. So what we need to do here is actually using the power rule and the chain rule, that's all. And this actually gives us a general fact about the extended power rule, meaning that if you want to take the derivative of fx power r, then using the chain rule, that is the product of r times fx power r minus 1 times the derivative of f of x, that's all. So now if we look back at the previous problem, then fx in that case is 3x plus 2. Then using this, we can easily see that the only thing that we can have to compute is the d over dx of 3x plus 2, which is 3. Okay, so this allows us to apply the extended power rule in order to compute the derivative of 3x plus 2 power r. Okay, so we start the lecture with a moving car. And then it just makes sense to close the lecture with that car again. We now talk about accelerations. Okay, so what do we mean by acceleration? Well, we already defined the velocity or the speed of the car, and we see that the speed of the car is also another function. And then we're going to talk about how fast is the speed changing. Well, for example, we say that from the beginning to t0, the speed going up, it increases. And after that, from t0 onward, the speed decrease. And we can also compare speed between various times. And now we can actually talking about the rate of change of the speed, which actually give us the definition of acceleration. So the rate of change of the speed is actually the derivative of the speed function vt, and we note by at that derivative, and we call that the acceleration. So what actually does that mean, acceleration? It actually tells us the speed at which the speed of the car is changing. So for example, if you listen or if you see some kind of review about car, you might see a feature that we name acceleration. We can talk about a car that increase the speed from 0 to 100 kilometers per hour in 3 seconds, 4 seconds, 5 seconds or something. So the shorter the time, the better the value of the car. Okay, so that is actually acceleration. And why is it useful? Because actually when you drive a car, well, and you want to get past the car in front or some hindrance thing in front, then you need to make sure that your car will get to a required speed that is greater than the speed of the car in front in order to get past the car. So you might need to care about the speed, or maybe the time that your car get from the current speed to the speed that required to pass the car in front. And the faster the acceleration, the easier you can get spot that other car, and that explains the value of the car. And you see that the car with better acceleration is normally cost more than the car with lower accelerations. Well, but that actually not what we that is not what we actually care about this course. We only care about the fact that, well, at, the acceleration, is actually the derivative of v, and in term v is actually the derivative of the distant function s. So we can actually guess to the acceleration by taking the derivative of the distant function twice. This is actually the definition of higher order derivative. So instead of taking the distant function now, we take a general function, and let's take a look at the other example. Here we choose f(x) to be x power 4, then the derivative of f is actually 4 times x power 3, which is another function, right? So you can again take the derivative of 4 power x 3, which is 12 times x squared. Okay, so now you have the derivative of f, which is called the second derivative of f at x, and we might denote it by f double prime of x, or by d subscript 2y over dx squared. So that is the definition of the second derivative of f, and generally the nth derivative of f at x can be defined recursively by using the nth minus 1 derivative of f, meaning that if you take the derivative of the nth minus 1 derivative of f, you get the nth derivative of f. And for a small value of n, we can actually use the prime notation, which is quite convenient. And also, if you write y equal fx, you can also use the Leibniz notation dny over dxn for the nth derivative of f at x.